So before starting, just want to mention that I had a sore throat. So if I split out some word, please forgive me. So yeah, maybe I would like to know how many of you know that how much your communication is dependent on these protocols. By these protocols, I mean TLS, IPSec, and all those things, right?
You can raise your hand.
Okay, so yeah. Well, if you don't, then maybe our next slide can remind you about those things. So we'll start with TLS, right? So TLS is the name after SSL version 3.1, and this protocol adds up my first letter to HTTP, which obviously make it HTTPS, right? And most of you already know that all of our website verification is done through certificates and all those things via SSL and TLS certificates, right? And these are some of the numbers that put you to make it believe, and obviously because it's true, right? And if you see, we have 87.6% of the website uses the valid SSL certificate, and 96% of Chrome browsing time occurs over HTTP connections, right? So, but this is not the real crux, right? What I want you to focus on is on those algorithms that work behind the scenes in these protocols, right? And which are the elliptical curve based Diffie-Hellman and other certificates and all those things, right? We can see that ECDHE key exchange and all those things. So now let's move to the next slide, which is another protocol, QUIC, which is kind of interesting itself because QUIC is a combination of all the great protocols, and it makes the internet, all the protocols that make the internet till 2012, I guess, right? Yeah, so then QUIC came and it said, okay, we'll take care of all the TLS and all those things. And you need not to worry about all those things anymore, right? But still, we'll give you a chance, and the TLS thing can work underneath, right? So about here, if you will see, the 36%, around 36% of the website had OT's HTTP3 support, right? Which shows that they are ready to support it. And also, like about 9% of the websites include QUIC in their tech stack. So, and again, this catch is not about how much they are being used, but what is inside them running behind the scenes, right? It's again the same elliptical curve and the RSA. So it could seem boring because I'm just giving an intro about all the protocols. Shubham will deep dive into the more technical terms and the things that we're going to discuss further. So yeah, we have an IPSec, the mechanism that puts security on the IP layer, right? And again, over here, you will see the, algorithms are the same, elliptical curve and the RSA here again. And also this IPSec covers, like, it's about 25% of the services, VPN services work on IPSec itself. So yeah. Then SSH, you all must be using it and have heard it in your life at least once, and we use it a lot. And it has been used from 1995 when you use those lousy VMs, right? Which are a bit laggy, but every day some work. But you never get some time to focus on the protocols, like the algorithms that work behind the scenes, right? So again, it's the same, the elliptic curve and the RSA, all those things. So will not you bore much using the same terms again and again. So this is the last one, the OAuth, which is again, like, it has become the basis of accessing service data without having the real credentials for the first time. And a lot of big companies use it. For example, Google, Meta, and we have Apple, GitHub, and all those big companies. So, and again, the security behind it is RSA and elliptic curve. So I have already presented you with a pack of protocols and their not interesting numbers, but it's more about like, yes, I want you to aware of this fact that yes, not by solid figures, but from a broader perspective, you all have been aware of these things which I already told right now. So, so like I just want the reason behind mentioning these protocols is their internal algorithm configuration is to remind you that how much they are dependent on the classical cryptography, right? Mainly RSA and elliptical curve. You can see in this diagram, from the whole security point of view, and with the recent development in the CRQC, which stands for cryptographically relevant quantum computers, was what we can say. It will be there within 10 to 20 years, which will be capable of breaking all these algorithms within minutes. So, yeah, the worst part is that in reality, we do not have these years because attacks like HNDL, you have heard about like harvest now, decrypt later, are a problem for the moment bad actors know that these exist, right? So, but that does not mean there is no progress to encounter this problem. So last year, NIST finally released for their first 3 PQ encryption standards. So major security bodies and organizations such as NSA, NCSC, and ISA, etc., start publishing their migration guidelines and have set the deadline till 2035. So, yeah, we have some standards for the migration as well. But even after this, the major problem persists. There are standards for PQC, but there is no PQ version of these major protocols, such as TLS, IPSec, and all those things, right? And and waiting for the complete standardization is an open arm invitation to HNDL type of attacks. So what should one do? Is there any way to prevent these attacks or any way to secure the things we are doing right now? So yeah, for sure there is. And that's why we are here. So instead for looking for the standards for the PQ version of these protocols, what we are planning to do is we can start by migrating the classical infra into the post-quantum infra itself. I mean, and for that one, you must need the basic, the code level knowledge and implementation of how it can be done, right? So this is what we are going to explain in the upcoming slides. So before that, just want to give you a short intro about me and my colleagues standing over there. So the most handsome one in the white jacket is me. I am S.Malik, and I'm the governing board representative of the Linux Foundation Networking. Along with that, I'm also the co-founder of one of our child community, NG-Core, and I'm also serving as a chief architect there. And I'm also the TSC member of 2 more projects in the Linux Foundation itself. And this guy is a great friend of mine and one of the tallest friend of mine. He's also a mentor at Linux Foundation Decentralized Trust and also one of the co-founder of the NG-Core community itself. So yeah, these are some of the topics we are going to cover today, and half of the topics I've already covered, which are just the basics. So before handing over to Shubham, I want to say that most of the work, I mean by most, I mean 99.99% of the work is done by Shubham itself, and I only done the 0.01% of the work by adding my profile picture in the slide. So yeah, over to you, Shubham, and thank you, everyone.
Okay, thanks, Shankar. So coming back to the topic. So this session is basically about a project that I started in my college. And so what I understand the problem is like you want to migrate your workloads from classical infrastructure to the post quantum alternatives, but you don't have any like base how you can start. What is like you don't have much of the implementations there. So what I believe, there's a gap in where like you can look at the code level, like how it happens between a client server communication, and similarly you can implement on your workloads, on your infrastructure and everything. So that's where I started a project, PQ Proto. So a little bit brief about this project. So it is a simple prototype that showcases like classical and post-quantum client-server communication, and it basically give you an idea like how the migration actually works for the classical, from the classical to the post-quantum alternative. And these are some of the protocols that it covers, like TLS and some of its variants, then QUIC, IPSec, and so on. Apart from that, like it has some, on the application level, there's like CLI-based communication where like you write something on the client side and it goes to the server, and server responds in the echo message. And some of the libraries which we use for the post-quantum implementations like OpenSSL, LibOQS, StrongSwan, and some other libraries for other protocols. So TLS. So it is like a cryptography protocol that encrypt everything on your internet. Okay, so it works over the TCP protocol at the transport layer, and it encrypts every packet that going above this TCP layer. And interesting part is that like OpenSSL also provide the guide how you can like write your own TCP connection. Apart from that, it has also a simple echo client server setup, like just like us, but we have a little better than them. Just joking, guys. So apart from that, like in this year, 2025, sorry. So in this year, like April, OpenSSL also has released a version 3.5 that has the native support of post-quantum cryptography, which is why we are using the basic functionality instead of going through the OQS provider and implement other post-quantum algorithms into our protocols. Okay, so these are like a quick overview, like what are the post-quantum algorithms in cryptography are supported by the TLS 1.3. Just to know, for the record, like TLS 1.3 only support the post-quantum cryptography in it. Nothing below that, like TLS, you cannot use the post-quantum cryptography below TLS 1.2 or anything. So like these are the cipher suits that TLS 1.3 uses, and these are the like KEM algorithms and signature algorithms. Like currently it has only 3 support, like ML-KEM and some hybrid ones, and then for the signatures it has like SLDSA and SLH-DSA and ML-DSA. Okay, so let's talk about like TLS connection, how it works on the code level. So first of all, you like set up a SSL context where you like that you configure like what is the minimum and maximum TLS configuration version. Then you also configure like signature algorithms and key exchange algorithm that needs to be supported, that will be used during the negotiation. Apart from that, like then you have loading the certificates and private keys and also verify it at the same time. Then you create a SSL object and linked it with either bio or some simple socket connections. And the main part, like handshake phase, it is basically you can't see it on the code level because it's happening in the background side, and it is mainly the main part. Like you send the client hello, then server hello, then actual client verification through certificates and everything. So this happens on the handshake part. Apart from that, in the application layer in our project, what we have done, like we have CLI-based communication. Again, you write something on the client side on the CLI, and it goes on the server side, and it echoes all the message back to the client. And again, the shutdown phase for the graceful shutdown. Like, okay, so this is like logs from our project. Like on the left side we have client, and on the right side we have the server. I have highlighted the configuration, like what are the certificates and what are the key parameters of the TLS connection. So on the certificate, we are using ML-DSA, and for the TLS connection, you can see like there we are using TLS version 1.2, some cipher source and hybrid key exchange, and ML-DSA for the signature. I want you to remember, like here in the TLS, we have only the certificate part on the server side, but in the mTLS, we will see same thing on the client side as well. So mTLS, again, a variant of the TLS, but it is similar to the standard TLS configuration, but a little difference, like you need client verification on the server side as well. For that, we use OpenSSL API SSL context set verify, which call back a function which handle all the verification related to the client. So here's another terminal screenshot. Like on the left side we have client, and on the right side we have servers. So you can see the server certificate and client. You can see the similar thing on both sides. Now both has certificate part on their end and having the same configuration for the mTLS connection, and it shows the same, like certificates we use ML-DSA and TLS 1.3. Okay, so DTLS, let's say it is a little different from the TLS, because TLS works upon like TCP for the reliability, whereas DTLS work upon UDP, which is basically for prioritizing the fastness and low latency. And apart from that, we also add a cookie secret to the verification for the SSL context, because like what happens, we cannot do all the process without verification. Otherwise, we can be a part of the DOS attack. So in order to mitigate this kind of attacks, we add cookie secret so that we verify the client before we actually do all the processes. And so currently, like OpenSSL does not have DTLS 1.3 support. It has on the different branch, which is DTLS 1.3. And it does not have like PQ support. So if you want to test it, you have to use like any provider, let's say OQS Provider with LibOQS and other alternatives. And apart from that, like what is the great news about it? Recently, Comcast also funded OpenSSL for the support of DTLS version 1.3. And the good news is that OpenSSL 3.6 are going to have DTLS 1.3 support. Okay, so another protocol, let's say QUIC. So previously, our whole internet works on these three protocols: TCP for the reliability, TLS for the encryption, and the HTTP2 for efficiency. But what this QUIC does after 2012, so QUIC basically squeeze all these protocols, all these layers functionality into one protocol and throw it into the internet. And basically, so this QUIC works over UDP. Why that so? To avoid the protocol ossification. So just to let you know, like protocol ossification is something, let's say you introduce some new protocol, but your internet middle boxes, such as routers, firewalls, net devices, they don't know about like your new protocol. And to adopt this protocol in every device on the internet is really, really hard. So what QUIC does, it build over the top of the UDP so that it can bypass these middle boxes on the internet and go back to your application without any problem. And the good part is that like OpenSSL has so many guides for the QUIC, for like working of QUIC over the HTTP1 and HTTP2. I would like to suggest like go for the HTTP3, because it was the thing that is going to be used in the internet so often. And for the prototype, I have used HTTP1, but yeah, go for the HTTP3. Okay, so these are some of the key functional elements that we have used for the QUIC connection. So SSL connect, first of all, we set up the SSL context with the like what method you want to use for the client or the server, and then there's a mandatory application protocol negotiation for the QUIC thing. So you have to set what application protocol you want to use. For the prototype, I've used HTTP1 instead of S3. And for then use biosockets to connect this SSL context to the sockets. And also that in QUIC you have options for single streams and multiple streams. Like you can open a listener and use that listener for the single connection, or either go for the multiple streams where you use single connection and create multiple streams over it for a good connection, like thing. And one more important thing that I noticed when I doing code part, like you have to first verify that the whole connection has been finished. Otherwise, it goes breakdown. Like due to the higher key sizes and everything, it takes more handshake time than usual than classical cryptography. So first of all, you have to check whether, let's say, handshake completion has been done or not. Okay, again, so this is like terminal logs for the QUIC connection. On the left side, we have client, and on the right side, we have server. We are having the QUIC connection parameters over here, and for the certificates, we have here. And one thing that you can notice, like we don't have certificate part on the client. You can also implement that as well. For now, we are using like simple TLS. You can go for the mTLS, where you have certificates on the client side as well. IPSec, your security over IP network. So before that, internet, like you have separate protocols for everything. Like you have PGP for encryption, decryption, and email, then SSL TLS certificate for web traffic, and SSH for remote access. But after that, I mean, like complete scene has been changed. So IPSec basically provides your security over the security, encryption, authentication, everything on the IP layer itself. And fortunately, we have an open source project that provides production level IPSec connection over any two entities. And for this project, we have used a Docker-based environment where we have client and server, and there's an IPSec connection between them in internal mode, and with using authentication configuration from like either pre-shared keys and or like certificate-based authentication. And what is the catch here? Like in the post-quantum setup for the pre-shared keys, we are using ML-KEM key exchange groups. And for the certificate authentication, we are using RSA certificates along with ML-KEM key exchange. Why that so? Because StrongSwan does not have currently the support for the post-quantum certificates, let's say ML-DSA. I mean, it has under development in another branch, but it is not mature enough. So I haven't tried it yet. So these are like what are the currently supported algorithms in IPSec-based, StrongSwan-based IPSec. So for this is like security association where you use ML-KEM for the key exchange. And on the left side, you can see what are the currently algorithms supported for the key exchange groups. So I've highlighted those ones PQ supported, and by the OpenSSL, we can incorporate more algorithms through other libraries like WolfSSL and so on. And a normal script like to test your CLI-based communication where you send messages from the client to the server side and the server echo back it to the client. Okay, so OAuth, I'm currently working on it. So basically, in order to access any third-party services, you need to have in order to access a third-party services without having the real conditions, you can use OAuth 2.0. And for that, we are using ORI Hydra and open source OAuth 2.0. It has support for the GWT access token. And for the PQ integration, we are planning to include like Cloudflare Circle and LibOQS Go for the ML-DSA support. But it's still on the working stage, so I haven't uploaded the code yet. Same for the SSH. I mean, like everyone knows about SSH. Like once in a life, they have done some kind of remote access from their system to some servers. And interesting fact is that like LibOQS also has a fork of OpenSSH, which provide a prototype of quantum resistant key exchange where they use ML-KEM for the security purposes. And again, yeah, we'll be going to use Cloudflare Circle for the post-quantum support, but it's still on the working stage. Okay, so let's come to the main part, like what are the challenges for the PQC migration? So there are like so much increase in the sizes of the certificates and keys. Like keys are almost 37 times higher in size, and like certificates are almost 50 times higher in storage. And one of the fact, like here, like in TLS connection, we have client hello, we have client hello. Inside the client hello, we have different parameters. Let's say cipher suits, keys, certificates, curve preferences, and so on. And with combined that, it bypass like maximum supported segment. So you have to split that into multiple segments and then transfer it to the other side of the connection. And something like, okay, so we don't have completely full PQC migration. I mean, we can't dependent on the full PQC migration, completely native support, because at any point it can fail. So we have to add a fallback mechanism for the hybrid methods. And then we have some like open source projects are good, but they are like immature, and they specify that we don't recommend it to use for the production because there may be vulnerabilities. So that's also kind of a challenge for us. And apart from that, due to like increase in key sizes, so in previous code, what we do, like we have assigned static allocation buffer for the RSA key, like 256, but now we have larger key sizes, so we have to change it, otherwise it may result in the buffer overflow. Okay. Okay, so what are the migration strategies and best practices we can follow? Okay, so identify the high-risk systems that are vulnerable to HNDL attacks and plan the migration accordingly. And again, like hybrid key exchange is also a challenge, and as well as also a best practice, because if your post-quantum supported key exchange fails, then you can fall back to your hybrid method, where it's still dependent on the classical cryptography for security of your system. Upgrade your CS software to issue PQC or hybrid certificates and handle large key sizes. Start with something small, then gradually expand it PQC support into your workloads. And apart from that, like do regular perform audits and detect like there's some side channel vulnerabilities unique to your PQC or not. Then again, measure your handshake latency, throughput, and resource overhead. And also, like you can use hardware and algorithm optimization, like let's say AES, NI, SIMD, and ADX to increase the performance of the cryptographic operations. Okay, so some of the real-world implementations. So some of the implementations, so we also have a background in the telecom side. So we have used that knowledge to implement some of the cryptography on that areas. So there are some projects like OpenAI, Open Air Interface. On the RAN side, we have implemented the PQ-MTLS over F1 AP between CU and DU, and PQ-MTLS over like SBI interface. Similarly, like these are some of the implementation we have done. I personally have patent on some of them. And this was one of the case, let's say the second one. PQ-MTLS 1.3 on service-based interface. So a little deeper in this, like PQ-MTLS on service-based interface is basically work upon the MTLS part. So for that, we have migrated some of the classical infrastructure. Let's say you can see the certificate signature algorithm and key exchange algorithm. We tried experimenting with post-quantum and hybrid algorithms so that we can see like this can be work or not. Using OpenSSL and LibOQS. And these are some of the logs. Like this is the log from NF, which are advertising its curve preferences, signatures, and based on that, the second one, the NRF, which is like a server which register the NF into its database. After complete connection, then we have RAN detection and connection establishment with the 5G core. And at the end of that, like your UE, like your mobile devices have a end-to-end connection from end-to-end PDU connection, which is basically how your whole mobile device work. Like you on your YouTube and have working internet and all. So this all a part of a PDU session. And these are some of the other real-world applications, like OQS has a number of users from Meta, from Google, and at so many things. And apart from that, Android had also incorporated LibOQS for its platform. Then Rel 10 package also has some implementation from LibOQS and OQS Provider. And like StrongSwan is also basically used in IPFire. It's a company which provided VPN-based services, and it is completely based on the StrongSwan with some modification. So thank you. This is it.
So
Open for.
Hi. Yeah, just a quick question. You mentioned in your one of the last slides, the application you did, you were talking about hybrid signature schemes. So which type of hybrid constructions were you using for signatures? Because on key establishment, the hybrid construction is somehow natural. You just put the two of them together. But on the hybrid signatures, there are multiple ways you can do that. Which construction specifically did you use?
Like this one? Okay, sorry. Okay, so you are talking about the implementation part?
No, what type of hybrid approach did you use? Like nested signatures, double nested signatures?
Basically, so signature we use ML-DSA part, ML-DSA, and for the key exchange part, we basically use like ML-KEM with some electrical curves.
No, but I mean, there it says hybrid ML-DSA with Edward curves. So do you first sign the message with the classical part and then sign the signature with the post-quantum part? Do you sign the message with both of them and then verify them? Which type of hybrid was?
Like I mean, like a little bit old about it, but like we directly sign it with this hybrid hybrid algorithm for the certificates.
Okay, thank you.
Anyone has more questions? Oh, okay. So thank you, Shabum and Shankar.
Yeah. Thank you.